Hello, welcome to the short lectures in physics. The present topic for discussion is indirect measurement methods. In physics, we understand that uh, there are three fundamental physical quantities that need to be measured: length, mass, and time. As far as the length is concerned, they can be measured with the ordinary scale, that is a ruler what we use in our home, to an accuracy of millimeters, or a measuring tape of few meters to an accuracy of millimeters. Both we use in the house front, and in the labs we use for better accuracy and better finer final final finer measurements can be done using vernier calipers or a screw gauge. In vernier calipers, a fraction of a millimeter can be measured accurately, 0.01 millimeters you can measure. In screw gauge, the accuracy can be achieved to a few microns. And then LVDT, linear variable differential transformer. Here also you can use the measurements can be done up to few microns accuracy. And these are the direct measurements for the length dimension. There are indirect methods which directly you cannot measure for measuring the large and very small dimensions of inaccessible objects. When it comes to the mass is a measure of inertia, and larger the mass, the more the inertia difficult to move, because inertia refers to the resistance offered by the body for changing its position. Coming to the dimension of mass m, conventionally we can measure the weights under the influence of gravitational force in a physical balance, which has got an arm, and two points are attached to the lever arm, and then in one of the arms we keep the object for which whose mass has to be determined, and the other one a known mass is kept. Both are under the both experience the gravitational force, hence the weight what we are measuring is known as gravitational mass mg. So it measures the mass against the gravity, that is mass at rest. And we can measure the mass using a spring also. The spring, when it is when a spring is uh, attached to a mass, the spring extends. So for different mass values, how much the spring is extending, you can calibrate, and you can achieve a spring constant K, which is nothing but the extension produced for a unit force. So the, the X is the extension, and because of the force N acting on the spring, so when unknown mass is attached, you can measure the extension, and using F is equal to Kx, you can determine the mass attached to this. And there is another method of measuring the mass is called inertial mass, and this mass is independent of the gravity, where that means it can be used even in microgravity condition, like in space stations where there is no gravitational force. Here the mass is set into vibration, and when it is vibrating, the time period of oscillation, that is time taken for one oscillation, is measured. So different masses can be subjected to vibration, and then the time period of oscillations can be measured, and graphs can be made for the known as calibration plots. Uh, that square of the time versus the mass, whatever we are doing. So using these calibration plots, we can determine the mass for which the time period has been determined experimentally. So this is initial mass and used for microgravity conditions also. If the oscillations are done using a spring, then also you can use time period is given by root m by k, where k is the spring constant and m is the mass. So using the time period value, you can determine the mass, inertial masses. Also, we can determine the mass using the force equation. Force is equal to mass into acceleration. So when a known force is acting on the body and it causes acceleration in the body, then F is equal to ma. So the inertial mass is given by the ratio of force to the acceleration produced in the body. So when mass is same on at any place, the weight is not so. It varies depending on the g value, that is gravitational force of the planet, and g is a variable thing, mass is a fixed thing. And the time dimensions can be measured using ordinary clocks, what we use in our houses, mechanical clocks, which measure seconds, hours, and minutes. And the electrical oscillators do rotations of the synchronous motor, or quartz watches can also be used for determining the time periods. And then for measuring the very small time periods of picoseconds to 10 to the power minus 12 seconds, the atomic class can be used. And when we know that nuclear materials, some unstable elements, nuclear elements, immediately they decay, they have decay times of different times. So a very short times can be measured using unstable element decay method, that is 10 to the power minus 16 to 10 to the power minus 24 seconds. Time measurements can be done using the unstable element, nuclear element decays. Also, large time periods of thousands of years can be measured using radioactive dating. That means like fossils and carbon and bones, etc., can be found in the earth, and then their lifetime can be measured using the nuclear activity present in the material as on that day, and compared with the original nuclear activity of the material. Hence, the, depending on the amount decayed, the lifetime of that fossil or the bone or another article can be found. Then, when, after completing the direct measurement, having an idea about direct measurement, now we'll go for indirect measurements, especially the uh, lengthwise dimensions. We'll discuss more on lengthwise discussions. So here we discuss about the large dimensions, very large things which you cannot access easily and then determine. So here you can use like echo method is first thing, that is sound waves are produced in front of the object which is very far, which you cannot access like a mountain, cliff or something like that. There you can stand in front of that and give a clap, then the sound waves travel towards the cliff and then come back to you and then hear as an echo. So the sound travels at the speed of the sound, and it travels twice the distance between the source, the person who is making the sound, and the clip. So the distance between the source and the object is given by x is equal to half vt, where v is the velocity of sound and t is the time taken by the sound to go to the cliff and then come back to the source. That is the time taken to receive the signal by the source after creation. Then sonars. Sonar is to generally used to determine, it is a ultrasound, again sound waves, ultrasound of different frequency, and they will be sent from the ship and then they are used to determine the depth of the sea or the submerged bodies. Here also the velocity, the sounds, ultrasound is created, it will go under the sea and then reflect back from the object and received by the source. So again the distance, the depth of the sea or whatever it is, or the submerged body can be given by half of velocity into time. So this how the depth of the sea can be estimated. And laser. Laser is a light source but high intense, and it has a monochromatic, that is single wavelength light, and unidirection. It travels straight unless otherwise it is disturbed beam. Here also, from the source, the light travels to the object and gets reflected back. So the distance between the source and the object is given by half the product of velocity of light in time, half ct. So you will get the distance from the source to the object. Radars are same procedure, but here we use the radio waves, and they are used for astronomical body distances, that is celestial body distances. And here also same method. The sound, the radio waves travel from the source to the object and they return back. So the distance between the source and the object is given by half the c into t. C is the velocity of the radio waves and t is the time to receive the signal by the source. Then, if you want to determine the size of the celestial bodies which are very large and very far, you can use this celestial bodies size can be determined. So most of the celestial bodies look like a circular shape. So from the point of observation on the Earth, you can focus your sextant to measure the sextant is an angle measuring device. You can measure the angle at the made from the point of observation at the two edges of the celestial body, whatever you are observing. So the distance between the two points on the celestial body is small d, and the distance from the body to the point of observation is capital D. Then using simple principles, the distance cap small d size of the body can be given as the product of distance d capital D into theta. Theta is the angle subtended by the body at the point of observation on the earth, as shown in the figure. So capital D is the distance from the celestial body to the point of observation, which already is known. That in the next slide we will see how to measure that. So small d can be, the size of the object can be estimated in this way. This is one the indirect method. Parallax method. Parallax error, as most of us know that, while taking readings on the traveling microscope, or we are obvious most of the times we face this parallax error because the angle at which you are looking at the reading matters much. If the angle of view is large, then the error is less, and if it is less, then the error is more. That means if you look from this angle, the point of observation will be different. If you see from this angle, it will be different. If you see straight, the error is minimum. So angle 90, your reading is perfect. If your angle is 10 degrees, 30 degrees, 40 degrees, then with the horizontal, then your error is more. This is parallax error. Same thing we see when we pass when we are moving in train or bus or something like that. Nearby bodies will be objects will move faster as compared to the farther objects. That means the error is less. The parallax error will be less for the farther objects and more for the nearer objects. So this is useful in finding large distances of the celestial bodies. Let us see how this works. Here, because the body is very far, you can consider it as a point at the point O is the celestial body, and A and B are two observation points on the Earth separated by a distance x. That capital D is the distance between the celestial body and the Earth's surface. So the x is a chord and theta is very small angle. So parallax error is the parallax error means the object is not moving at all. So the distance between the two observation points to the celestial body is same, capital D. Hence, from the simple trigonometrical principles, the distance between the two observation points are given by the product of d into theta. So theta, so to observe the angle angle of elevation from the point A and point B, the observation points on the earth, and the difference of these angle of elevations theta is the angle subtended by the body with the arc length of x. So x is equal to d theta, then the object distance capital D is equal to x by theta. X is already known because we are the distance between the two observation points A and B is known. Angular difference theta is also known from the angle of elevation measurements made from A points A and B. And then one important thing is the observation should be made simultaneously from points A and B observation points in this method. Then, if you have a large building whose height has to be determined, very difficult to use a method to determine the height of the building, top building like PQ. And what you can use a shadow method using triangulation method. So you can cast its shadow when sun is behind the building. Its shadow is cast on the floor. PO. PO is the shadow of the building PQ. So its edge is at O. So now you take a small pole whose height is known, whose length dimension is known, height of the pole is known, and move it from point O towards the building till the pole's shadow RS shadow edge also matches with the point O, coincides with the point O. Then from the triangle ORS, angle of elevation can be theta can be determined. Theta is estimated. So tan theta is equal to RS by OR. Because triangle OPQ and ORS are identical from the simple trigonometric principles, the height of the building PQ can be estimated from the known values of OP, RS and OR. So height of the object PQ is given by OR by RS by OR into OP. All the terms are known in this. That's how the building height is determined on a sunny day. If the sunlight is not there, night times, then you can directly measure the angle of elevation from the point O, theta, using this extent, and then tan theta is equal to PQ by OP, and hence PQ, that is height of the building, is equal to OP, distance between the point of observation to the foot of the building P, into tan theta. So this is how the building height can be estimated. And some inaccessible building height means we can measure the distance from the foot of the building to the point of observation. Suppose if the foot of the building or object is not accessible, like a mountain as seen in this figure, that is inaccessible object's height measurement. But only if you see a hill, only its peak can be seen from anywhere. So what you do in this case is, PQ is the height of the mountain you have to measure. Make to go away from the mountain to points R and S away. So the distance between R and S are known, though we don't know what is QR or QS, but RS distance is known. So make angle of elevations of the peak of the mountain or hill from points observation points R and S. Let theta 1 and theta 2 are the respective angles of elevation. Then cot theta 1 is given by QR by OPQ, and cot theta 2 is given by QS by PQ. Here QR and QS are not measurable. So then the object height is given by QS minus QR into cot theta 2 minus cot theta 1. QS minus QR is nothing but RS, the distance between the two points of observation known. So RS into cot theta 2, cot theta 2, theta 1 values are also known. Hence the height of the mountain can be measured. Then last but not the least is the river width measurement. So river width measurements also, there are two banks for the river. So at one bank you place fix a pole in vertical position at point P, and then on the other bank just opposite to the point P at point Q you fix another pole, and then from Q you move along the river bank on the opposite side of P. From Q you move to R, and then there you fix another pole vertically. Then move from R to point T along the bank, and then away from the bank from T to S, and till you fix another pole in vertical position at the point S, such that the poles, all the three poles positioned at point P, point R and point S all lie in one line. That means you are making two identical triangles PQR and RST. So the angles PRQ and TRS are same as theta. Then tan theta is given by PQ by QR, which is equal to TS by TR. Thus all QR, RT, TS are all known. Then PQ is equal to TS by TR by QR. These are the river width measurements are done. This technique is used even by civil engineers in surveying methods. Thank you. Hope this uh, lecture is useful to you in understanding the indirect measurement of dimensions. See you in the next lecture. Bye.